so because the subject is more arithmetic than geometry, so let me start with a very classical motivating theorem by Jigel. It's a classical theorem on elliptic curve. So let's consider an elliptic curve over rational numbers q, such that the rational points of this elliptic curve is infinite, and consider a non-constant morphism to projective line phi. So let's consider this morphism phi as a coordinate function on E. So for example, if E is a y-axis transform of on the projective plane, so phi can be, for example, projection to the x coordinate. So, and for a point of x, for a point of E, let us write phi of x as a pair of coprime integer a and b. So because this is a rational point, we can always write phi of x in this form. So a and b are integers with GCD is equal to 1. So the theorem says the asymptotically the size of these coordinates are the same. So precisely the ratio of log of the modulus of each coordinate goes to 1 if we make the maximum of the absolute value of the coordinates goes to infinity. So this theorem is a classical theorem, and this can be considered as a quantitative version of the fact that there are only finitely many integral points on an elliptic curve. So there are infinitely many rational points, but there are only finitely many integral points. And here I say integral point is the points of like this form. So this is an integer, and the second coordinate is 1. So this kind of point is called integral points, and there are only finitely many integral points on elliptic curve. So, and this theorem is a kind of quantitative version of this statement. Okay, so it is often the case that if we have a theorem, this kind of theorem on elliptic curve or abelian variety, we can consider the dynamic version of this kind of theorem. So, and actually, Silverman proves a dynamic version of this theorem. So this is a dynamical version of Ziegel's theorem. So let's consider now a rational surjective endomorphism on projective line of degree d at least 2, and consider a point x with infinite f orbit. So this corresponds to the elliptic curve has infinite points, we assumed. And now we assume that this point is infinite orbit. And we, as before, we write the coordinate fn of x with coprime integers a and b. And here we need additional assumption. So we assume that secondary of f is not the form of this form. It's not this form. So so in other words, the secondary of f is not a polynomial map on projective line with respect to the point 0 or infinity, right? So P is a homogeneous polynomial, and so if secondary is this form, the secondary is we can consider it an endomorphism A1, and it is called polynomial map. And so we assume if the secondary is not a polynomial map, then the conclusion is the same. So log of the modulus of coordinates and take the ratio, then we and the ratio goes to 1 as n goes to infinity. So and like before, we can conclude that there are only finitely many integral points in the orbit of x. Okay, so this is a theorem by Tsubama, and this is also we can say this is also classical because it's more or less 30 years ago. Okay, so let's look at some examples. So actually, this is non-example. So the assumption on the secondary is actually necessary. So let's consider this power map of P1. So, and consider the orbit of T2 and 3. So we can calculate the orbit in this form, and the ratio in the statement goes to log 2 divided by log 3, and which is not equal to 1, of course. Okay, so this is non-example. And the example is, so this is, I constructed randomly. This is a degree 2 map on P1, and consider the orbit of 0 and 1. So the numerical calculation shows that the coordinates grows like this, and look at the this beautiful exponential growth of the digit, and the ratio of the log of each coordinate is converges to 1. So this is 0.98 after 6 iterates. So it's converges very fast. So this is a theorem by Silverman. All right. So so Silverman deduced this kind of theorem from another theorem, so which involves height functions and so-called distance function. So here height function comes into the story. So first, let me so in order to state Silverman's second theorem, we have to introduce some notion on so-called distance function and height function. Maybe some of you are very familiar with height functions, but let me recall what height function is. So first, distance function. This is a more local one. So delta, this is a map from P1 cross P1 to R. Strictly speaking, we actually allowed value infinity. So this is the delta is defined in this way, but this looks ugly for the first look. So let me explain more down to earth way. So this is roughly speaking, this is a log plus of 1 over distance between these points. Distance between, so say, let me call this point X and this point Y, distance between X and Y. And here, log plus is maximum of 0 and log. Okay, so distance function is actually a negative log of distance. So it behaves more like variation. So this way, so distance, so negative log of distance is kind of way to get a variation from absolute value. So this is this behaves more like a variation, but we call this distance function on projective line. And another ingredient is a height function. So this is a height function. This is a definition of height function on P1. So here K is a number field. K is a number field. So this is the finite extension of Q. And the height of this point is defined as the sum of log of maximum of absolute values. This sum runs over all absolute values of K. So if K is a rational number, V is a usual absolute value or periodic absolute values. And and this sum is actually a finite sum, so we get a well-defined function on P1, and we can actually extend this to all algebraic points on P1. So this is a height function, and this, roughly speaking, this measures the arithmetic complexity of algebraic points.
Sorry for the interrupt.
Yeah.
I asked a question. So for the height function, I remember there is you need to add the degree of the extension.
Yeah, but yeah, that's right. But I normalize this absolute value so that we don't need the. Okay, so that's a probable convention. So if you prefer, you can add this form, but we can also use this kind of normalization. Right.
Okay.
So,
okay.
This kind of normalization. So this is a problem of normalization, so it doesn't really matter. But yeah, so but this kind of trick is important to define.
If you divide by the degree, you will get this is called a absolute logarithm function. So there is a absolute before the logarithm function. If you don't have this degree function, just the height function.
Oh, sorry, what degree function? What is?
If you take the normalization, then this function is called the absolute logarithm height function. Otherwise, it's just a logarithm height function.
Yeah. So that is also a matter of normalization of the absolute value. So
yeah, that's a definition. Yeah, if you call it by degree, it's called absolute logarithm function.
Oh, okay. I see. Oh, yeah. Yeah.
Yeah,
but
it's not definition.
Yeah. That's a matter of normalization. Yeah. Yes. Thank you. But anyway, we have to care about the normalization of absolute values. Okay. So, but in this talk, I'm mostly work over a fixed number field, so we don't need to really care about this normalization. Okay, so having defined these notions, let me introduce the second theorem on Silverman. So, and this theorem is what I want to generalize the higher dimension case. So let's consider an endomorphism on P1 over a number field K, and assume that the degree of f is larger than or equal to 2, and take a point x and y on P1, a rational point on P1. So, and assume that the pre-image of y under f is consists of at least 2 points. So, which means, in other words, f is not totally ramified over y. So, okay. So this is a condition on ramification of the form of f. And the second assumption is the orbit of x is infinite. And fix an embedding of k into C so that we can talk about the distance function. So recall that the distance function is we define the distance function by using the absolute value of C. So we have to embed k into C, or in other words, we have to choose an absolute value, choose an Archimedean absolute value on k. And the conclusion is the distance function divided by ample height function goes to 0 as n goes to infinity. So let me explain the meaning of the theorems a little bit. So the distance function, recall that this distance function is log plus of 1 over distance. So this theorem says the orbit of x doesn't get close to y as fast as the height grows, right? So the orbit could be very close to y, but the speed of getting closer and closer to y is bounded by this growth. And one more remark is this is far from true in transcendental setting. So what I mean transcendental is over C, we can also talk about the distance function because we only use the usual absolute values. And but the height function is a purely arithmetic thing. But in this setting, this grows like d to the n. D is the degree of f. So we can talk about the limit of this this kind of ratio. And this is not this doesn't go to 0 under these assumptions. So even if y is is not a critical point of f and x, even if y is for example a point where at which f is not ramified, and for such a y, there are uncountably many x such that this doesn't go to 0. And so this is also pointed out in the paper by Silverman. So this is purely arithmetic statement, and this is a very non-trivial. Okay, so let me sketch why this kind of local height thing. Oh, so do you see theorem by Silverman? I guess the connection is interrupted.
I can see the whiteboard.
Okay, so let me. Okay, let me try again. All right.
Oh, I guess it's okay.
So do you see? Okay. Okay. So this is a theorem by Silverman which involves height functions, and let me briefly sketch why this kind of height estimate implies the size of coordinates or such an arithmetic thing. So just a sketch. So let's consider this ratio. So this is a distance divided by ample height function. And we wrote the orbitals A and P, so we just plug in. And by the definition of height functions, delta and H, we can rewrite this in this form. So this is a ratio of log of some function involving coordinates. And we simplify this in this form. Okay, so the second theorem says this goes to 0 with some exceptions. So, oh, sorry. Okay. So, so this goes to 0, which means this part goes to 1. Okay. So the conclusion is the limit of this ratio goes to 1. Okay. And instead of plugging in 0, 1, we can also plug in 1, 0. Then we get here B. Okay. We get B here. So we have two ratios that both goes to 1, and so that concludes that actually this log of an and log of bn are symptotically the same. So this is a proof. Okay, so here, so far this is a story of one-dimensional dynamics and very classical, and also this is very classical story. So let me talk about higher dimensional generalizations. So what is higher dimensional generalization? What is possible? What kind of questions we can ask about this kind of phenomenon? So we considered endomorphism P1, but in higher dimensional case, we want to consider any kind of endomorphism on any kind of variety. But in this talk, we are going to assume that X is geometrically irreducible smooth projective variety. We assume smoothness. And also the height function is also defined in higher dimensional case in the very same way, So there are notion of ample height function on projective varieties. So this is this is maybe you're familiar with this notion. And the distance function. So there are actually notion of arithmetic distance function on any projective variety. This is also introduced by Yohsuke. But we can also talk about a local height function associated with a closed subscheme Y. So I will be explaining what local height function associated with Y in the next slide. Let me give us some comment on what kind of question we are going to talk about. So a very natural question is what is the behavior of this kind of sequence that goes to infinity? So this is a main question in this talk. Okay, so but talking about this kind of question, let me first introduce the notion of a local height function associated with subscheme. Okay, so this is our setting. So X is a projective variety of a number field, and Y is a proper closed subscheme. So Y could be a divisor on X. And MK, so this is a set of absolute values on K. Oh, sorry. Oh, I touched the wrong place. Sorry. Okay, sorry. Yeah. Okay, so yeah, MK is a set of absolute values on K. Okay, so I'm not going to give the formal definition of local height function because it's a kind of complicated formula. So but the concept is very simple. So a local height function associated with y, and I'm going to write it lambda sub y, is roughly log plus of 1 over dyadic distance between x and y. So v is some fixed some absolute value on k, and so the local height function with entry x and v is this measures how x close to y. So if x is close to y, it's getting bigger and bigger, and if x is far from y, it's gonna 0, right? It's gonna be 0. So here log plus, this is just notice log plus is the maximum of log and 0. All right, so this is defined on this set x minus y, and on y we sometimes allow lambda y. On y we sometimes set the value of local height function to be infinity. Okay, so this is local height function. And the global height function on y is just the sum of local height function over the absolute values, all absolute values. And this is actually finite sum, and we can define.
Sorry, can we extend this function to the whole space X? Because
no, we can. No, we cannot extend. So if X is the convention is this is infinity if y. All right. So.
But because for the height function, you can always define it on the whole space.
Oh, okay. Oh, that's a good point. I will explain the trick in the next slide. Okay. So, but for a subscheme, we cannot extend. We actually cannot extend in total space, even for global height function. Actually, for Cartier divisors we can extend, but for subschemes we cannot extend. Okay. So. All right, so this is global height function. So let me remark something. Okay, so this is our definition. And if y is a Cartier divisor, effective Cartier divisor, so then we know there are a so-called wave height machine. So we have another definition. It's actually the same definition. So hy is in our definition is actually the same thing that you call wave height function on x minus d, because we only define h sub y on x minus d. But if d is a Cartier divisor, not necessarily effective, we can actually extend hd on the whole space. And this is because the global height function is independent of the linear equivalence. But for subvarieties, the global height function h sub y, this really depends on the class of y, or anyways any kind of. So for example, if y and y prime are rationally equivalent, this is not true up to bounded functions, even for up to bounded functions. So this is a problem. So this I will be explaining later, but so the height function associated with subscheme is really arithmetic stuff. So anyway, so for Cartier divisors we can extend to the whole space, but for subvariety we cannot do this. And the third remark, this is actually a definition of distance function. So distance function is defined just the local height function associated with diagonal. So this measures the distance from the diagonal, and so we can also consider the distance between these 2 points, 2 entries. Okay, but note that if we fix the second entry of the distance function, this is equal to the local height function associated with y. So as long as we fix the second entry, we don't need to consider distance function. We only need to consider local height function. Okay, so I'm going to use only lambda sub blah blah blah. Okay, so these are remarks on local height functions. Okay, so let me propose a question on subscheme versus ample height function in the context of arithmetic dynamics. So this is our setting. F is a surjective morphism on the projective variety. The Y is a proper cross subscheme. So the Y can be a Cauchy divisor. And H sub H is a fixed ample height function on X. So H is an ample divisor on X. So, and this is a height function on X. And take a rational point on X. Okay, so the first question is, let's consider the ratio of closed height associated with closed subscheme and the ample height function, and consider the behavior of this ratio on the orbit Fn of x, and take the limit. So under what condition this limit goes to 0? So this is the first question. And the second question is, let's consider a finite collection of absolute values. So the question is, consider the ratio of the sum of local height function over some finite collection of absolute values divided by ample height function, and under what condition this ratio goes to 0 as n goes to infinity. So so by the definition, hy is the sum of local height function. So if we know this limit goes to 0, of course this limit also goes to 0, right? But even if this limit doesn't go to 0, this limit can be 0. So I rather want to consider these questions separately. So the below is not a sub question of the first one. Okay, so let me show you some motivations motivations of these questions. Okay, so the first one is okay. So why do we care about the global height function of this form? So X is our original variety. So we usually equip this with an endomorphism F. When we study arithmetic dynamics of this kind of map, we usually encounter this situation. So G is a rational map from X to another variety, and we sometimes want to know this kind of function, the behavior of this kind of function. So this is an ample height function on X prime. So this is a pullback of ample height function to X by a rational map. So when you study arithmetic dynamics, we usually want to know this kind of function, the behavior of this kind of function on the orbit, and this function is can be written roughly in this form. So HD is a usual height function. HD is a usual height function. So D is a Cauchy divisor, and but this is not exactly equal to a Bay height function. So there are error terms coming from indeterminacy locus of G. So this is indeterminacy locus of G. So this is a subset codimension 2 usually. So and when you study this kind of function, this term is always an abstraction. So that's why I want to know this kind of function in the context of arithmetic dynamics. Okay, so this is a motivation from arithmetic dynamics. And the second motivation is I just want to make sure that the question is sometimes very, very arithmetic, could be arithmetic, or sometimes could be purely arithmetic. So let's consider a particular endomorphism on P2. So this is defined by this way. So x, y, z goes to a times x, b times y, and z. Here a and b are multiplicatively independent integers. And let's consider local height function associated with this point. So then this statement, so this ratio goes to 0, is actually equivalent to this ratio goes to 0. So this is just by definition. This is just by just plugging in definitions of these functions, and we get we can easily see that this statement is equivalent to this statement. And this is a very, very highly non-trivial theorem by Peugeot, Corbet, and Zanier. So the proof involves like Schmidt subspace theorem. So this is a really arithmetic thing. But here our F is automorphism, so there are no geometric contributions. So the problem becomes purely arithmetic. Okay, so sorry. Yeah, and these are a motivation for global height function. So what about local height function? So of course, h sub y is the sum of local height function. So this partial sum approximate the global height function. So understanding this sum is kind of first step to understand global height function. So we can consider this is a proximity part of global height function. So that's one motivation. But there are other motivations to consider this kind of function. So as I told you in the beginning, there are some application to integral points on orbits or more strongly size of coordinates of orbits and etc. So there are some arithmetic motivation to consider this kind of function. Okay, so let me briefly mention the previous works on this kind of thing. This statement. So of course, the starting point was Silvermont's theorem. So when x is p1 and s is an Archimedean absolute value, so the Silvermont theorem answers the question fully in local setting, local question. And when x is a projective space and y is a divisor, there are a series of papers by Yohsuke on this limit and application to integral points. But his theorem mainly mostly assume Voigt's conjecture on projective space. The Voigt's conjecture is a famous, very huge conjecture in arithmetic dynamics, like termination of flips in Diophantine world. Okay, so let me move on to main theorems. So this is our setting. X is going to be a smooth projective variety over K, geometrically irreducible. And F is a surjective morphism on K over K, and H sub H is an ample height function. Right? So and by technical reason, we take always H sub H larger than or equal to 1. Okay, so this is our setting. The first theorem is concerning the case that y is a zero-dimensional subvariety. So let's take a point y. This is a rational point on x, and fix a local height function lambda sub y, right? And take another rational point x that we consider the orbit of x. And suppose first that the ample height function grows exponentially. So in other words, the alpha sub of x, which I call it arithmetic degree, and so this is defined by the exponential growth rate ample height function along the orbit. And this limit always exists because our variety is projective and f is a morphism. And we assume that this is larger than 1. Okay, so the ample height function grows very fast. This is the first assumption. The second assumption is this is a slightly complicated assumption. This corresponds to the ramification condition on F. So there are assume that there are no F periodic subvarieties P in X such that the point Y to which we attach a local height function, the point Y is contained in P, and another condition. So I will be explaining what E of P is in the next slide. So, but for now, just think this is a invariant that measure how F badly ramified on P, on the orbit of P. So this is kind of multiplicity of F at P, and we assume that there are no such subvariety, such periodic subvariety. Then the conclusion is the limit in the question goes to 0. Okay, so let me explain the definition of this guy. So I don't know the widely accepted name of this invariant, but okay. Okay, so let C be a scheme point. This is a scheme theoretic point. So this could be a generic point. So the EF of C is a multiplicity of F at C. So this is out in local ring because our map F is finite. So and E is the length of this module, this out in local ring. And EX of plus C is the average of this guy. So this is a sort of average multiplicity of F at C. And the existence of this limit is actually very non-trivial. It involves a lot of things. And this is, I guess, it's first grouped by in the thesis of Shari Faber. I don't know, maybe. Yeah. And this is just a notation. So for subvariety P, E of P is defined by taking a generic point of E to P for P, and we define it in this way. Okay, so this is just a notation. Okay, so let me remark something. So first of all, we have a chain rule for multiplicities. So this is just a chain rule of first course calculus. So, but we need F to be flat morphism for this chain rule. Okay, and if C is a periodic of period R, actually the existence of this limit is elementary. Just follow from the definition, and this is equal to the geometric mean of multiplicities of F at the cycle of C, right? So this is a geometric mean of multiplicities. So let's go back to our main theorem. So the main theorem says, this theorem says if Y is not contained in periodic subvariety at which F is highly ramified. So if Y is contained in such subvariety, some orbit could be attracted to such kind of periodic subvariety, and then we cannot expect this kind of limit goes to 0. So this is a really necessary assumption. Okay, so then we can say that if n of x, the orbit doesn't get close to the point y as fast as the height function grows. Okay, so and actually this theorem applied to projective line, this recovers Silverman's theorem. Okay, so this is really a generalization of Silverman's theorem. All right, so this is a case that y is a point. So what about y has dimension? Y has positive dimension. Okay, so that is next main theorem. Okay, so let's consider a proper subvariety of x, any dimension, and as before, a fixed local height function hy. Okay, and suppose, as before, the arithmetic degree, so the exponential growth rate of the orbit of x, exponential growth rate of ample height function around the orbit is larger than 1. And by technical reason, we have to assume that the orbit is generic. So this is the definition of generic is the intersection with any proper growth subscheme subset is finite for any growth subset. Okay, so we can reformulate this theorem without the assumption of genericness, but for simplicity, I'm going to assume that the orbit is generic. Okay, so so this is a new assumption, and 3 is a assumption on ramification. So there are no F periodics of variety P such that P intersect with Y and the same condition E is larger than or equal to alpha. Okay, and further, we actually need Voitas conjecture. So this is again, this is a huge conjecture in Diophantine approximation. So I'll be little talk about this conjecture later. But the conclusion is the same. So this limit goes to 0 in local case. Okay, so these are main theorems, and I'm gonna sketch the proof later. But before doing so, let me give some fun. Let me show you some fun corollaries. Okay, so size of coordinates. So this is a really fun part of doing arithmetic dynamics, personally. So let's consider surjective endomorphism on projective space defined over Q, and the degree is at least 2. Okay, so as before, let's write the orbit in this way. So A0 to AN are integers, coprime integers. The first corollary is this one. This is a corollary of theorem A. Okay, so assume some ramification conditions. Okay, so but this will be satisfied for a randomly chosen F in experience. Then this ratio. So the numerator is log of maximum of coordinates, but we don't take all coordinates, so 0 to n minus 1. Okay, and the denominator we take all coordinates, and the ratio goes to 1. So this is kind of generalization of Silberman's size of coordinates theorem. Okay, so and if we assume Voitas conjecture, we can say more. So this is again condition ramifications, some conditions, some obvious conditions, and we also assume orbit is generic. Then we can say that the coordinates, the size of coordinates are the same. So log of maximum or log of the first coordinate divided by log of the maximum of all coordinates goes to 1. So this says this basically says every coordinates grows in the same speed. If we choose a dynamical system randomly enough, and the point is randomly enough. Okay, so this is an example. So you don't need to understand what the map is. So this is a really complicated map. But by numerical calculation, so looking at the point 2, 3, and -4, the size of this log of the absolute value. So this is more or less the digit of the coordinate, the size of digit. It grows. The first coordinate grows like this, and the second and third coordinate grows faster and faster. And this map actually satisfies the assumptions on the first corollary. So let me go back. So that map F satisfies the assumption of this part, but doesn't satisfy this part. So so this part, this coordinate grows less faster than the second and third coordinate. Okay. And this is really random map. So I constructed this map randomly, and let's look at the point or the orbit of the point 1, 1, 1. Then the size of coordinates grows like this, and after 10th iterate, these are more or less the same. Okay, so although the second corollary is conditional of Voitas conjecture, but this numerical calculation shows that is true. So anyway, so this is what the theorem and the corollary says. Okay, so let me give a sketch of idea of proof of theorem, the main theorem A. And theorem B, the proof of theorem B goes more or less the same lines. Okay, so Oh, okay. So so far, do you have any questions so far? So these are right. Okay, so let me go into the proof of the theorem. So remember that this is our goal. This is our goal. And because this is just a finite sum, we only need to prove that for each v, the limit goes to 0. Okay. And for simplicity, we write this guy just lambda sub y of x. Okay. So fix 2 point x and y, and by technical reason, I have to assume h is a variable. Okay, so by factoriality, by usual factoriality of height functions, to put compatibility with pullback. So you want to know this guy. We can bound this guy in this form. So this is a local height function of pullback preimage of y, and here gamma 0 of k. This is just a constant. There's some constant depending on k, some integer k. And because this preimage consists of several points, we break up into sum of local height function associated with each point, and we need some constant. So this is ramification. This is multiplicity of f to the k at each point z in the preimage. Okay, so and we again have a constant depending on k. And pick up a point z such that this local height function is take the maximum. So this is a maximum term. So this is going to be the term of this sum. And the other term is actually bounded by some constant that depends on k. Okay, so the upshot is we get this inequality. Okay, so just dividing by the ample height function. So we want to know this limit. This guy goes to 0. So and we can bound this guy by this function. And note that this is bounded from below by 0. So we only need to show that this goes to 0. And this part is fine. This is the easy part because at the very last end of the proof, we are going to fix k, large k, and after that we make n very large. So this part goes to 0. This is the easy part. This is difficult part. So in order to bound this part, we need 3 ingredients because there are 3 terms. Okay. And so this is what we have proven. And the first ingredient is from Diophantine approximation. This is Ross theorem, so-called Ross theorem. So this fancy version of Ross theorem. So this is not the one you may find on like Wikipedia. But this is also a Ross theorem. So the theorem says this local height function can be bounded by 3 times very ample height function on this set. So, and there are some exceptions of this inequality, but this is a finite set. And the important point is that this coefficient 3 is independent of this point. The dependence of this point only appears in this exceptional corrections of operation of the inequality. Okay, so this is first ingredient. And actually, Ross theorem says we can take this constant 3. We can actually take this 2 plus some small number, but we only need 3. Okay, the second ingredient is asymptotic bound of multiplicities. So this is a purely geometric part of this proof. So this is due to Faber and Guignac, and this is somehow so-called equidistribution on Noetherian topological space. So we have defined EF sub plus, but we also define EF sub minus negative. So this is this limit, and let's look at this. So y is the original point, our original point, and take a preimage, case preimage of y, So Z is a preimage of Y, and take the ramification, multiplicity of f to the k at Z, and take the maximum. And finally, take the case root of this quantity, okay? And take the limit. Okay, so Gignac proves that this limit exists, and the existence of this limit ultimately depends on the Shari favors existence of EF plus. So that's why I wrote here favor. And Gignac also proves that this limit is actually equal to this this quantity. So this is somehow appeared in the main theorem. So this is maximum of the geometric mean of multiplicity of f at P, where P is a periodic subvariety. So this kind of controls the multiplicity in the backward orbit. Okay. And by our assumption, this is strictly bounded by arithmetic degree. So this is almost due to the Gignac. Okay, so upshot is if we take k large enough, then the multiplicity of the preimage divided by alpha to the k is very small. So epsilon is a very small number. Okay, for Z. So this doesn't depend on the specific choice of Z submax. Okay, all right. So this is a second ingredient. And the third ingredient is growth of ample height function. So this is due to Kawaguchi-Silverman's Jordan canonical height and some work of Sano. So there are constant C1, C2, depending only on F, and constant integer L depends on point X, such that the growth of ample height function can be written in this form. So we need here alpha is larger than 1. If alpha is larger than 1, the ample height grows like this. Okay, so we have 3 ingredients here. So the first is Ross theorem. The second is control of multiplicity due to Gignac favor, and height growth due to Sano. Okay, so this is inequality, and this is our 3 ingredient. So let's conclude our proof. So first, take a small number epsilon. This is really epsilon delta argument. So take a epsilon, and take k large enough so that we have this inequality. Okay, so we can take k. We take k so that we can ignore the multiplicity part. So okay, so let's bound this guy. So first we plug in. So this is what we have proven. So let's first bound this part. Okay, so this part is bounded by Ross theorem. Okay, so we replace this part by 3 times ample height function. Okay. And second, we use the height estimate. Okay, so this is height estimate. And we plug in this formula into this part and this part. Okay, so it looks ugly, but just plug in this inequality and simplify this into this form. So we ignore this part, and so here is n minus k, and here we got n. So we have alpha to the k in the denominator. The numerator is multiplicity. Okay, so now we can bound this part by the choice of k. So we've got we bound this guy by epsilon times some constant, which is independent of epsilon, plus some constant, plus some term. Okay, so as we fix k, if we make n large enough, we can also ignore this part. So this is bounded by some constant times epsilon, and we are done. So this is a proof of our main theorem. Okay, so this is an idea of proof of. This is a slightly detailed proof of theorem A. So let me just sketch a proof of theorem B. So there are some interesting ingredients in this proof of theorem B. So the idea is more or less the same. But in the higher dimensional case, if y has positive dimension, we have to bound this local height function. But if y has positive dimension, this is very likely to be irreducible. So the preimage of y could be singular but irreducible. So in order to bound this guy, we need Voitas conjecture, and I displayed here some variant of Voitas conjecture. So usual Voitas conjecture involves a simple normal crossing divisor on some variety, but by usual Voitas conjecture, which we can actually show a singular version, that involves low canonical threshold of a pair x and this subvariety. So this is a log canonical threshold of x, and strictly speaking, the ideal sheaf of the subvariety. Okay, and this term times the local height function is bounded by some height function with some exceptions. We have some exceptions also. So this falls on open subset on the total variety. Okay. So and again, the point is that the constant and this k and epsilon is independent of this subvariety.
So you take the reduced part.
No, I don't take the reduced part. This could be reduced, non-reduced scheme.
So inverse scheme theoretic
Oh yeah, this is scheme theoretic inverse. Sorry. Yeah. So this is scheme theory.
Okay.
So so this could be very small. The low canonical threshold could be very, very small, right? So we have to bound the low canonical threshold from below as k grows. So that is again, we use Guignac's theorem. So we can actually prove a lower bound of low canonical threshold in this way. So this is so the lim info low canonical threshold to the 1 over case root of low canonical threshold is bounded below by this quantity. So EF negative of y is like a average multiplicity in the preimage of backward orbit of y. So this is also bounded. So this can be written in another way. So by using a periodic subvariety containing y. But we can bound this. But anyway, we have a bound in terms of multiplicities. Right. So this involves just the low canonical threshold and multiplicity, the relation between low canonical threshold and multiplicity, and then we use Guignac's theorem to bound the multiplicity from below. Okay, so that's the idea of the proof of theorem B. Okay. All right. So thank you. So I stop here.
Okay, thank you very much. Okay, so any questions?
Yeah, Yohsuke. So in the proof of theorem A, so how to see your gamma 0, gamma 1 is independent of n?
Oh, gamma. Okay.
Yeah. So
Constant
at the very beginning, you gamma 0, you have
Oh yeah. Okay. I see. I understand the equation. Okay, in this slide. So this gamma, right?
Yeah.
Okay. So this inequality actually comes from a punctorial property of local height function.
So it depends on the map. Or...
Yeah. That's right. Depends on map. Yeah. So here we apply this to okay. So this depends on K, but this doesn't depend on the point X. And gamma 1 is also the same reason. So, and this part is actually a little bit tricky. We consider the preimage of Y, so this consists of some points. And our orbit might be here. This is f to the n minus k of x. So we pick up this point. This is z max. Okay, so this is z max. The other points are far away from this z max, but the distance between these points only depends on k and y. Right. So strictly speaking, this gamma 2 depends on k and y. Okay. Okay, that's okay. But that doesn't depend on n. So there are some there are some points that we have to be careful about depending on n. Okay, thanks.
Okay, so I have a question. I'm considering about your condition in your CMA. Can you change to the slide?
Okay, yeah. Theorem A.
Yeah. You have two conditions. One is arithmetic degree is greater than 1, and the second condition a little bit longer. So, yeah. So I'm wondering, what if your P is a divisor, is a prime divisor? For example, your X is just a P1 or just a curve, P is just a point. So the second condition, does it mean that P will be totally periodic or something like this? If
sorry, so what?
If your second condition, your EF plus P greater or equal than alpha fx, if P is a divisor, I guess this implies P is totally periodic or not.
I see. Yeah. If I see. So if alpha is equal to, so let's consider only projective space.
Yeah, it's just a Pn, yeah. And the P is a hyperplane or something like this.
Okay, so and alpha, in this case, alpha is a degree of the algebraic degree of.
Yeah.
Okay, so in this case, yeah, that's right. So
because in general, the ramification index of a divisor will be smaller than the.
Yeah. So this condition says P is totally.
And you also assume it is a periodic, so it has to be totally periodic.
Totally periodic, yeah, and that forces that our map F is a kind of polynomial map, so the map on the affine space. Yeah.
And also, okay. So,
yeah,
and also a question: what in general, it is very easy to find the point Y in your space, in your X, satisfying your condition 2. How many points satisfying P?
I think so. I guess if we randomly pick up a point, then that's going to satisfy these conditions. So
you mean open dense subset?
Yeah, that is what I want to know. That is one thing I want to know. But
so etal is okay, right? On ramified,
yeah, that's
F
right.
is on ramified, okay.
Yeah. If it's etal, then there is no such sub-ITP. So we only need the first condition. Yeah, that's also that's a very good question. So
okay,
I actually don't know what. Yeah, so I don't know what kind of. I don't know what kind of P for a given F. I don't know the way to list up all such P's. It's for a very specific example, yeah, we can do that. You can do that.
I guess you may have many Y, but I don't know how many of them.
Yeah.
It is.
Yeah. So this P must be contained. So not necessarily this, but the period of the P forms the orbit of P forms a cycle, and one of them must be contained in the ramification divisor of F. So in practice, I usually look at the ramification divisor and consider if it is periodic or not. So in most cases, open dense subset, in the open dense subset, we can apply this. Yeah, that's an interesting question, but I can't, yeah, but I don't know the answer for now.
Any other question? Okay, if no, let's thank the speaker again. Okay, thank you.
Thank you.
Okay, so I guess I guess I cannot record the video here because since the staff will help me maybe. I don't know. I don't have the button like the Euro. Yeah.
Hi, sir.
Yeah,
you have a question?
You didn't need the right to record.
Okay.
Maybe.
I guess the staff can help me maybe. Okay, it's not so important. Okay, anyway. Okay, thank you again.